this video, we will explore some practical examples of ALMA tuning setups when spectral line observing is your primary science goal. We'll also look at some common issues you may encounter. If you are new to ALMA, you may want to check out our related videos shown here.
ALMA is capable of detecting a myriad of emission lines from molecular species in the local and high redshift universe. ALMA's correlator is versatile enough to target multiple spectral lines with different spectral resolutions. Before we get into specific examples, let's briefly review a few important points.
First, let's look at the radiometer equation, which says that the noise level in an ALMA observation depends directly on the system noise of the telescope and inversely on the square root of the bandwidth times the integration time. When calculating the required time on source, you will first need to decide what signal-to-noise ratio you want. The signal-to-noise ratio is just the expected signal strength divided by the expected noise, also described as the sensitivity.
As an example, suppose your spectral line was expected to have a peak intensity of 100 millijanskis, and you needed a signal-to-noise ratio of 20 in order to model your data. This means you'd need to achieve a noise level, or sensitivity, of 5 millijanskis in order to achieve the desired signal-to-noise ratio. You will also need to tell the observing tool, or OT, which bandwidth to use for this calculation. Depending on your science requirements, you may need to use a bandwidth as narrow as a single channel to ensure sufficient velocity resolution to model the spectral line. Wider widths can be specified by using the user-defined bandwidth settings in the OT if averaging of channels is needed to improve sensitivity. For example, if you just want to detect weak spectral lines. Armed with your required sensitivity and bandwidth, the OT will calculate the integration time you need.
Another important consideration for spectral line observations is the radial velocity of an astronomical source. Whether its velocity comes from your source moving through space or from cosmological expansion, these motions will induce a redshift or blue shift in your source's observed spectrum. The OT will use the rest frequency of your observations and your source velocity to calculate the observed frequency for your target, and will then tune the receiver to match that observed frequency. If you don't list the correct source velocity in the OT, you risk missing your target line entirely, especially for fast-moving or high redshift sources.
Now let's explore the various ways ALMA's correlator can be configured for spectral line observing. Most science observations focused on spectral lines will be configured with the spectral line option in the OT. As we discussed in our Principles and Components video, up to 16 spectral windows can be specified in a given tuning of the local oscillator, or LO. This is done by subdividing the spectral window in a baseband into two halves, and each half window can also be split into two quarter windows. Spectral averaging can be applied to each spectral window individually in cases where the specified narrow channel width is not needed for all the targeted lines, or to allow some windows to sample the continuum.
With so many choices, setups typically are done by first arranging spectral windows appropriate to your most important lines of interest. These choices will constrain which additional lines of interest can be observed. Be aware that it may be a challenge to observe all of the lines in one tuning.
Finally, it is important to note that centering two spectral windows on the same line will not improve the line sensitivity, because this does not increase the number of photons collected by the receivers.
Now, let's look at some examples of tuning setups to cover multiple spectral lines. The simplest and most straightforward approach is to center one baseband with one spectral window on each spectral line of interest, with remaining basebands, if any, set up for continuum. However, lines less than 2 GHz apart may be observed within the same baseband, and you have some options.
In this case, you may want to take advantage of the ability to split a spectral window into 2, 3, or 4 sub-windows and place each window over a line. However, if you have many lines, this may not be feasible. In these cases, you can use a single spectral window to cover multiple lines, or overlap spectral windows to provide contiguous coverage and frequency. To cover all of these lines, however, it is important to make sure that your channel width is not too wide for the expected line width for each species, but also not too narrow for the sensitivity you need.
Be careful not to place your spectral line too close to the edge of your spectral window, because correcting for the Earth's Doppler motion could shift the line partly outside of the spectral window. It's also wise not to place your spectral windows too close to the edge of the baseband, because the sensitivity drops rapidly at the baseband edge. The OT will give you a warning when this happens.
If your science case needs to detect more spectral lines than a single tuning can provide, you have 2 options. The first is to request multiple tunings per target, which might be useful if, for instance, you want to observe at both the lower frequency end and the higher frequency end of band 6, or with multiple receiver bands.
A second option exists if you want to fill in most or all of the frequency space over a wide range of frequencies within a single receiver band. In this case, you can select the spectral scan option in the OT and select the tuning range and resolution that you require. Spectral scans are particularly useful for projects involving line surveys. In spectral scan mode, ALMA will change the frequency of the LO up to 5 times, allowing you to sequentially observe up to 5 different ranges of frequency space. The OT will select LO frequencies that overlap the sideband coverage between each shift, ensuring continuous frequency coverage within the requested range.
Many more specialized tuning setups are available than we have covered here. We also anticipate offering even greater flexibility and frequency coverage as ALMA's upcoming wideband sensitivity upgrade is complete. Check out the ALMA primer for more tuning examples, and don't be afraid to test several tuning setups in the OT to decide which works best for your project.
We have just taken a brief look at some tips and examples of how to set up spectral line observations with ALMA. Be sure to check out our other videos, some of which are linked here.
Happy tuning!